All right, everybody, let's talk about homework for chapter 13. Let's walk through this. And you guys should be able to see my screen. All right, so a couple things to remember, just some FYI stuff. The factorial design is a research design in which participants are observed across all combinations of levels of two or more factors. The two-way ANOVA is a statistical procedure used to test hypotheses concerning the variance of groups created by combining the levels of two factors. This test is used when the variance in any one population is unknown. Each cell is a group created by the unique combination of one level from each factor. Hence, the total number of cells, or PQ, is equal to the total number of groups in a study. A between subject design for a two-way ANOVA is used when different participants are observed in each group created by combining the levels of two factors. A cell is the combination of one level from each factor. Each cell is a group in a research study. A complete factorial design is a research design in which each level of one factor is combined or crossed with each level of the other factor, with participants observed in each cell or combination of levels. A between subjects factor is a type of factor in which different participants are observed at each level of the factor. A within subjects factor is a type of factor in which the same participants are observed across the levels of the factor. A two between design or between subjects design is a research design in which different participants are observed in each group created by combining the levels of two factors. Example one, when we combine the levels of two between subjects factors, we use the two between, only two E's, or between subjects design. In this design, different participants are observed in each group by combining the levels of the two factors. An example of one such study from an area of research on the training and effectiveness of military decision-making can be shown in this example. Suppose we record the decision-making ability of military veterans from three branches of the armed services. Factor A, who hold different ranks, factor B. The following table shows a structure of 3x2 between subjects ANOVA with 5 participants observed in each cell or group. And here it is. 5 enlisted officers, Army, Navy, Marines, 5 officers. So enlisted like a grunt, like you're not in charge of anybody, okay? And then officer, 5, 5, and 5 in the Army, Navy, and Marines. Therefore, if we look at this table, you could look at it like 5, 10, 15, 20, 25, 30. That's one way to look at it. However, we want to look at it slightly different. So for a two-way ANOVA, the N is the number of participants per cell or group, N is the total number of participants in a study. Using the between subjects design, we can thus determine the total number of participants in the study N, in the study by multiplying N by the number of levels in each factor, PQ. The total number of participants of N is equal to NPQ. N is equal to 5, we got that from here because there's 5, okay, in our group. P is equal to 3 because we have 3 different branches of service, and Q is equal to 2, enlisted or officer. So we multiply those together, and the total number of participants between using this between subjects design is N is equal to 5. So there's 5, okay, times 3 times 2 times 30. And this is an extra table, so we'll just delete that right now. That should look like that. So now perform the same aforementioned steps with the following data. And just for the sake of simplicity, we'll just change this to make these all 7 for everybody, just because that makes it, I think, easier. So, and we'll say N is equal to 42, like that, okay? But I want you to figure that out using that formula, okay? So our next one is a one between one within design or mixed design is a research design in which different participants are observed at each level of the between subjects factor, and the same participants are observed across the levels of the within subjects factor. When we combine the levels of between subjects factor and one within subjects factor, we use the one between, one within, or mixed design. In this design, different participants are observed at each level of a between subjects factor, and the same participants are observed across the labels of a within subjects factor. An example of one such study from an area of research on the role of parents and teachers as authority figures and mentors. Suppose we report how often students at each class level seek advice from different types of authority figures, factor B. Factor A is the level of each class, factor B is the different types of authority. So this shows, the following table below shows a structure of a 4x2 mixed ANOVA with 5 participants observed in each cell or group. So really, I'm glad I changed that, because up here, it's just easier if it's always the same, okay? It gets more complicated if it's not the same, so we'll just run with that. So actually, let me just pause this and I'll update that. All right, back to where we were, everybody. Back to our screen share. So we have 5 people observed in each group, the parent and the teacher. Using a mixed design, we determine the total number of participants in a study by multiplying the number of levels of the between subjects factor in this example. So we multiply n equals 5 by 4 class levels. The total number of participants in this mixed design is 5 times 4 is 20. So now calculate the total number of participants using a mixed design in the example below. Same thing, and we're going to say n is 24, but use that calculation, okay, that I just showed you. And we will stop this for just. All right, let's go back to where we were, guys, and here we go. So some FYI stuff. Within subjects design for a 2A ANOVA is used when the same participants are observed in each group, combining the levels of the 2 factors. A 2 within design or within subjects design is a research design in which the same participants are observed in each group, created by combining the levels of 2 factors. The 2-way between subjects ANOVA is a statistical procedure used to test the hypotheses concerning the combination of levels of 2 factors using the 2 between or 2 between subjects design. A main effect is a source of variation associated with the mean differences across levels of a single factor. The more sugar people consume, increased exposure, the more they tend to like sugary foods. As an example from this area of research, suppose a researcher hypothesizes that a person's level of sugar exposure can interfere or distract him or her during a computer task when food is present. To test this, the researcher uses the estimated daily intake sugar scale for sugar to group participants by their level of exposure to sugars, low, moderate, or high. All participants then complete a computer task at a table with a buffet of sugary foods, buffet present, or a stack of papers, buffet absent on the table. Slower times to complete the computer task indicate a greater interference or distraction. The duration of time it took participants to complete the computer task in each group are given in the table below. We will compute the 2-way between subjects ANOVA to analyze the significance of using a 0.05 level of significance. So here is our table. Now, this table I also have right here for you. That's right. This table is also an Excel file, so please make sure you're looking at that Excel file. And that Excel file looks kind of like that. And let's do our share. Here we go. Why is it doing that? Okay. All right. And let's go into our share. Now, I made this so that you could scroll down So as you're going through the Word document, look at the examples, pausing me, however you're going through the information here, I put everything in order from top to bottom. So this is just like the same table. These right here are our means, okay? You can always get your mean real easily if you just take and you type in, if you ever want to do the mean in Excel, it's pretty easy to type in mean, and then you just type in the range. If I want the mean of these, I just go like that. Right, what happened there? Equals mean. Is it the average? No. Average is the mean. Average of these numbers like this. And that gives you 11, okay? So it's equals average and it'll tell you what it is. You could do that if you wanted to check the math. That's just a trick on the mean with Excel in terms of the formula. So let's go back to our Word document here and walk through this a little bit more. And where's my screen share? Okay. So step one, what we're always going to want to do is we always want to state the hypothesis. So we're going to start with stating the hypotheses. Boy, I really got spelling errors today. State the hypotheses. The null hypothesis states that the group means for exposure to sugar's main effect, buffet main effect, and both factors combined interaction do not vary, which means your variance is nothing is equal to 0 in the population. The alternative hypothesis states that the group means do vary, the variance is greater than 0. So we write the null hypothesis out like this. Mean times to complete the task do not vary by exposure to sugars, buffet, and or the combination of these two factors. And then our alternative hypothesis, we write out like this. And our alternative hypothesis is mean times to complete the computer task do vary by exposure to sugars, buffet, and or the combination of these two factors. Step two, we want to set the criteria for a decision. The level of significance in this test is 0.05. We must compute the degrees of freedom to find the critical values for each hypothesis test. There are 4 sources of variation in the two-way between subjects ANOVA. Remember, ANOVA is simply just analysis of variance. And we compute degrees of freedom for each source for the variation. So the first one is the degrees of freedom for factor A or exposure are P minus 1. Therefore, degrees of freedom A is 3 minus 1, which is equal to 2. The degrees of freedom for factor B, buffet, are Q minus 1. So the degrees of freedom B is 2 minus 1 is equal to 1. To compute the degrees of freedom for the A by B interaction, we multiply the degrees of freedom by factor A by the degrees of freedom for factor B, P minus 1 times Q minus 1. So the degrees of freedom A times B is 2 times 1 is equal to 2. The degrees of freedom error are the total number of cells technical difficulties here. Just trying to keep my self lit up here. Okay, there we go. Is equal to 2. So therefore, the degrees of freedom error are the total number of cells PQ multiplied by the degrees of freedom for each cell, n minus 1 or PQ n minus 1. Therefore, the degrees of freedom error is equal to 3 times 2 times 6 minus 1, which is equal to 30. The total degrees of freedom are equal to the total number of participants minus 1, which are the degrees of freedom for variance, n minus 1 or npq minus 1. We can add up the degrees of freedom we just computed or calculate npq minus 1 to find the total degrees of freedom. Degrees of freedom total is 2 plus 1 plus 2 plus 30 is equal to 35, or the other way we can look at it is degrees of freedom total is 6 times 3 times 2 minus 1 is equal to 35. Remember, PEMDAS is our acronym, PEMDAS, the order of operations. That's why you get 35. We will compute 3 hypothesis tests, 1 for each main effect and 1 for the interaction. Each hypothesis test requires a different critical value. We will find critical values for each of the hypotheses tests in step 4, because that will make it easier to see why the crucial values are computed differently for each test if we wait until step 4 to find the critical values. Step 3, compute the test statistic. For each hypothesis test, we compute the F statistic. The F statistic can be used to determine the total variance attributed to factor A or exposure, factor B, buffet, to the combinations of factors A and B relative to the variance attributed to error. We compute the test statistic for each hypothesis using a 4-stage process similar to that used for one-way ANOVAs. So we have to do the preliminary calculations. We're going to find the sum of the values in each cell. That's what it says. Yeah, it seems to say that's, I think when you see this like that, I think sigma. I think put that further down here. So find the sum of the value in each cell across each row and column, and NP, and Q. These preliminary calculations are shown in the accompanying Excel worksheet and in the table above. So find N, P, and Q. I should not say PL. The number of participants per cell is N equals 6. So where did we get that from? N equals 6. It should be right up here on our table, right? 1, 2, 3, 4, 5, 6. That's where that came from, because there's 6 right here. Okay, that's not just some random thing out of the air. That's exactly where we found 6. So let's look at our next thing here. Our next thing is exposure to sugars is factor A, the phase factor B, hence equals 3, the levels of factor A, low, moderate, high. And Q, the levels of factor B, the total number of participants in the study is, therefore, NPQ is 36 participants. So the next thing we got to do is sum these. So the way we do that is, let me go ahead and show you Excel here. And I went ahead and gave you some of the information already out there so that you could just sort of walk yourself through the formulas while you're working on that. So let's stop our share here. Let's go into Excel. And just to explain a little bit more, because I feel like maybe B, where I got the P from was not clear. So if you look at this right here, as soon as this opens up, I'm sure why it's delayed, but give it a second. Absent or present, that's where that came from. Okay, the two different conditions, that's where I got that from. Okay, just so you guys are on the same page there. Okay, so the next thing we want to look at is we want to sum our totals here. Let's go back actually. I'm sure if, let's see if you have. Let's put that back to desktop 2. Let's see if we can show you the Word document. Explain N, P, and Q. And then for our Word document, this will come up. So Q are the 2 levels, P are the 3 conditions, okay? And there's 6 people. There's 6 people that are exposed. Low, medium, high is P, and Q are the 2 levels of absent sugar and no sugar, okay? Just to be clear on where that information is coming from, so that you're not thinking it's completely just like out of nowhere, okay? So now let's go back to what we have to do. We have to find all of these. We have to total these up. So let's go back to our Excel file and let's go back to a share so you guys can see that. So what we did what I did to make the calculations easy for everybody is I went in here for our two-way ANOVA. And why this is not pulling up right away, I'm not sure, but that's okay. Okay, so now give it a second. It's going to look wonky for a second. And then here we go. Okay, so let's scroll down here. Okay. And here we have our table, okay? So what we did is did a couple different things to make it easy. And this is something you're going to want to do when you're figuring these out. So we have all of our low scores, okay? This is our N is 6 people. I took our values, or X, and I summed them. Sum of the values, 54. That's all that is right here. The next thing I did is I just did it for all of them. Our moderates, don't worry about these squares yet if you're looking at those, okay? Moderate, we took all of these values, some of them we got 60. High, took all of these values, some of them we got 66. That's for the absent condition. Then I did the same thing with present. I summed all of these, got the sum of the values, summed all the moderate, and if it'd be easier, we could just write low, moderate, high, just so you have that, just so that's right in front of you, okay? And you might as well write the squared right here too, just so you have it. Don't worry about squared yet, I'll explain that in a moment. Okay, so then I just summed all these, sum of the values, sum of the values, sum of the values. Next, I took and I squared all of these values. So 8 times 8 is 64, 7 times 7 is 49. I squared all these, and then I got the sum of the values right here. 502, 650, 748 for the absent condition, sum of the values squared, excuse me, for the present condition. Like that, that's where those came from. Then this right here, the sum of the total was the sum of all of these. So I took the 54 and 36 and I got 90. This one, 54 plus, so the two conditions, that's that sum right there. Same thing right here, 60, 60, 120, 66, and 84, 150. Then I took and I added these, each 190, 120, 150, 360 total. Then this last one was all of the squares totaled. So we started with this one right here. Right here. So we took all of these. So we took all of these right here. 1, 2, 3, 4, 5, 6. And we got a total. So that's a total of all of the squares. So it's that one, that one, that one, that one, that one, and that one. Okay, so that's all done for you. Now don't worry about filling this table in yet. Just wanted to make sense of where we got this information. All right, so the next thing we'll do is we'll go back to our share. And we'll go back to our Word document and walk through that a little bit more here. All right, so we'll pull this up so you guys can see that kind of completely here. Okay, so we did all of this just now. We just basically summed everything. Now we're going to do our intermediate calculations. So in stage, and as I'm doing this and walking through it, you might want to look at your Excel sheet, and maybe I can integrate that too here as we go through. So in stage 1, we computed the values needed to make calculations in stage 2. We will use the values we compute in stage 2 to find the sum of the squares for each source of variation in stage 3. There are 5 calculations. First, we compute a correction factor by squaring the grand total, the sum of the values total, and divided by the total sample size. So that was 360 squared, which I'm sure you could see in Excel, divided by 36. So that's equals 3,600. So 360 squared. So I think pretty well explained what NPQ was, but that 360 squared, I'm getting that right from, let's just go in here and kind of a smaller screen. And where is our Excel? I believe that's it right here. So that 360 squared came from right, where is that? Right here. So I took that and I squared it and I divided by the total, which is 36. So just give you guys a sense of where each value is coming from. So let's go back to our Word document. And we'll make that big again, and then we'll, okay. So that's 360 squared divided by 36, which is 3,600. Second, we restate the sum of all the squared scores. So if you remember in the Excel sheet, and feel free to pause, the total of all the squares was 3,954. I'm just restating that number. Third, we are going to calculate the variation attributed to factor A exposure by dividing the sum of the squared scores in each column, total A, by the number of scores summed in each column n cubed. So that is going to be 90 squared plus 120 squared plus 150 squared divided by 6 times 2, which is 3750. Again, pulling all these values right out of Excel. Fourth, we calculate the variation attributed to factor B, or the buffet, by dividing the sum of the squared scores in each row B by the total number of scores summed in each row NP. So the sum of B squared over NP is 180 squared plus 180 squared divided by NP 6 times 3. We get 3,600. Last, we calculate the variation attributed to the interaction exposure times buffet by dividing the sum of the squared scores in each cell total by the number of scores in each cell n. So this is what our formula looks like. Then we break that down. That's 54 squared plus 60 squared plus 66 squared plus 36 squared plus 60 squared plus 84 squared divided by 6 is equal to 3804. Stage 3. Computing the sum of the squares for each source of variation. The sum of the squares is the numerator for the variance. We will compute the variance, which is a mean square, for each main effect, the interaction, error, and the total. So we compute the sum of the squares for each source of variation and the sum of the squares total. The sum of the squares for factor A, SSA, sum of the squares factor A, is the difference between calculation 3, which we did earlier, and calculation 1. So the sum of the squares factor A, 3 minus 1 is 3750 minus 3600 is equal to 150. Next, we want to do the sum of the squares for factor B. Sum of the squares B is equal to 4 minus 1. So that's 3600 minus 3600, not 36,000, which is equal to 0. The sum of the squares for the A times B interactions is calculation 5 minus calculation 1 in stage 2 minus the sum of the squares for factors A and B. So the sum of the squares A and B times B is equal to 5 minus 1 minus sum of the squares A minus sum of the squares B, which is, we plug our numbers in, 3804 minus 3600 minus 150 minus 0 is equal to 54. Next, we do the sum of the squares error, which is the difference between calculation 2 and calculation 5 in stage 2. The sum of the squares error is 2 minus 5, which is 3,954 minus 3,804 is equal to 150. The sum of the squares total is the difference between calculation 2 and calculation 1 in stage 2. Therefore, the sum of the squares total is equal to 2 minus 1, which if we plug the numbers in, that's 3,954 minus 3,600 is equal to 354. Stage 4, completing the F table. The F table lists the sum of the squares, the degrees of freedom, the mean square, and the test statistic value for each hypothesis test. The calculations in the F table are described here and listed in the accompanying spreadsheet, which you have. The first column of values from the F table lists the sum of the squares. We computed these in stage 3. The second column lists the degrees of freedom. We computed these in step 2. And then we will use these values to compute the mean square or variance for each source of variation. The formula for the sum of the squares is divided by the degrees of freedom. So we divide across each row to compute the mean square. Note, the mean square error, or MSE, is the denominator for each hypothesis test. So just so you're not getting lost, let's just look at the table for Excel. So I probably didn't have to redo it, share, but we'll just share again. So what I'm talking about, ladies, is this right here. It's a little bit smaller, but let me, yep. And we'll go back to our two-way ANOVA assignment, which is right here. And what I'm talking about right here is this table right here. We've already calculated some of this, but here are our formulas. We're going to fill the table in a moment, but here are all of the formulas, okay? Which I'll walk you through in a moment. This table is here for the formulas. Like I said, scroll down, and that's how you stay on top of your stuff. The second set of data is further down, but let's just walk through this at the moment. And we probably did not have to stop screen sharing again, but that's okay. Back to our desktop too, and we'll go back to breaking it down. So let's make this a little bit smaller, and let's go back to our Word document. And we're right here. We're talking about completing the F table, okay, which is right here. So I believe I just had mentioned, note the mean square error is the denominator for each hypothesis test. Therefore, the variance or mean square for factor A is the mean square MSA, mean square for factor A, is the sum of the squares A divided by the degrees of freedom A. Therefore, that is 150. That's this number right here plugged in here. Okay, so I'm doing that and that divided by our degrees of freedom, A factor divided by 2, which equals 75. The variance or mean square error for factor B, so the mean square error factor B is sum of the squares B divided by degrees of freedom B. That is going to be 0 divided by 1, which of course is 0. The variance or mean square error for the A times B interaction is the mean sum of the mean square A times B is equal to the sum of the squares A times B divided by the degrees of freedom A times B. So we plug that in and we get 54 divided by 2, which is 27. The variance or mean square error, so mean square error is equal to the sum of the squares error divided by degrees of freedom error. We plug our numbers in, that's 150 divided by 30, which is equal to 5. The test statistic is basically the same as that for the one-way ANOVAs. It is a mean square between groups divided by the mean square error. For a two-way between subjects ANOVA, we compute a different hypothesis test for each source between groups variation, one for each main effect or one for the interaction. The test statistic for factor A exposure is the mean square A divided by the mean square error. So that's 75 divided by 5, which is 15. Now, to find the critical value, we need to know the degrees of freedom for factor A and for the error. The degrees of freedom numerator for factor A is 2. The degrees of freedom denominator for error is 30. We locate the critical value in the unit normal table, which is absolutely posted right in bright space at a 0.05 level of significance. The critical value associated with 2 and 30 degrees of freedom. So remember, you go into your table and you find 2 and then 30. And that is 3.32. So the test statistic for the factor B buffet, so factor B buffet, is equal to the mean square for B divided by the mean square error, okay? You plug that in, that's 0 divided by 5, so that's 0. To find the critical value, we need to know the degrees of freedom for factor B and for the error. The degrees of freedom error, the degrees of freedom numerator for factor B is 1. The degrees of freedom denominator for error does not change, so that's 30, which I mentioned previously in terms of the denominator not changing. At a 0.05 level of significance, the critical value associated with 1 and 30 degrees of freedom in the unit normal table is 4.17. Again, do those 2 different degrees in your unit normal table, your F table, and you'll see that it's 4.17. The test statistic for the A times B exposure buffet interaction is the mean square error, A times B, divided by the mean square error, which is 27 divided by 5, which is 5.40. Again, to find the critical value, we need to know the degrees of freedom for the A times B interaction for error. The degrees of freedom numerator for the interaction is 2. The degrees of freedom denominator for error, again, is not changed, it's still 30. At a 0.05 level of significance, the critical value associated with 2 and 30 degrees of freedom is given the unit normal table is 3.32. Next, we want to make a decision. We will make a decision for each hypothesis test by comparing the value of the test statistic to the critical value. The main effect of factor A, or exposure, is 15, which exceeds the critical value of 3.32. So we're going to reject the null hypothesis because it's higher, okay? This is bigger than 3.32. The main effect factor for factor B of buffet is not significant because it does not equal the critical value, does not exceed the critical value of 4.17. So we retain the null hypothesis because it equals, is that 0? Yeah, because that was 0, that's why. So it doesn't exceed 4.17, so we retain the null hypothesis. The A times B interaction, exposure times buffet, is significant because 5.40 exceeds the critical value of 3.32. So we reject the null hypothesis. Just trying to make sure we have enough light here for the recording, everybody. There we go. So now do the same procedure, the second set of data found in Excel. So just walk through the steps I just gave you, just step by step, rewind, pause, etc. And what we're talking about right here is back, I probably have to reshare again, but what we're talking about is if we make this smaller and we go back to Excel, as soon as it'll let us. So I filled all of those in for you already, which you can cross-reference, okay? Right here, okay? So we filled these all in, an asterisk. So those are all filled in. Here's our second set of data, but I squared everything for you and did your calculations to make that a little bit easier. Here's our table, here's our formulas, and then here's our blank table to fill in. So just fill that in and put your work in the Word document and put your answers in the Excel file. And that concludes the chapter 13 homework walkthrough. Hope you learned something, and I'll see you in the next video.